All right, now we do have our first midterms coming up on Wednesday of next week. Okay, so we have that coming up. Let's have a look at a 3D review, because a lot of the stuff we're going to deal with on that midterm will be 3D, and this is kind of we're kind of finished up a unit. We're not going to do too much more 3D. So if you're online, it's 3D review problem from 2014 from the Moodle page downloads. Okay, it's available there. So let's have a look, and there it is. It's down in the homework downloads down there a ways. I think so. You should be able to find it there. Looks like this. So let's have a look. So find, find some other students that you can work with if you'd like. We've got this shaft, and it's attached to the wall at B. And what we'd like to do would be to see if it's strong enough to take this force we're going to apply. So we're going to apply a force of 5,200 newtons to the shaft. Okay, now what we know about this shaft is it has allowable limits on it. It can handle 12,000 newtons of compression, 3,000 of tension, 6,000 of shear, and 22,000 newton meters of moment. So that's like the specs on it, the specifications, what it can do. Now keep in mind that when a manufacturer makes something like this, they don't have any idea what you're going to do with it. So they will just give you the strengths that they think the object has, okay? So this is what it can withstand, but they have no idea what you're gonna do with it. So they just tell you everything it can do. And these are the common things that they would rate it for, okay? So tension, compression, shear, and we also have a moment criteria on this. What I'd like to know is this shaft strong enough to handle that 5,200 newtons that's acting on it, okay? And what I would also like to know is what's the maximum allowable force in cable BC before the shaft fails? Okay, so how high of a force can you have in BC before the shaft fails? Okay, and what I'd like you to do would be to work through this in a logical way and show your work. You very likely might want to work with some people. You don't have to, but it's always good to have some study partners, I think, preferably your own major too. So if you work with people, just put them down there and put down their majors. And then let's just start working through this, okay? So what would the first thing to do be, you think? What's that now? Yeah, I think that's probably a good place to start. Get those coordinates, yeah. That's step number one. If you like, find some people you can work with. It's always good to, get some different points of view on this. Okay, those of you online, we do have a forum you can kind of ask questions on, but you can, ask questions of me too if you have them on this as well. Of course, if you're online, it's going to be a lot harder to find people to work with. I know that, but so this is just a review problem to work through. So I'm going to pause the recording here so you don't have to just listen to silence. But why don't you get the coordinates on A, B, and C, and then check back in after you have them, and we'll see what we got. All right, so there's the coordinates there. All right, so the next thing, whenever I see a force in a vector like that, I want to get a force vector, right? So go through that process. Yep. Okay, because I'm sorry now.
Turn into a unit vector in the direction of the arrows and multiply it times 2.
So yeah, the next thing is to find the force from B to C. Get that into a vector form. We could check that too, because we want to be sure we got that right before we do the rest of the stuff. Okay, there's the force vector. So now remember, you can have a little bit of difference from me. It isn't like my answer is perfect. If you're within 1% of my answer, you're good, right? So negative 2581, 1095, and 4380. That's what I got for that force vector. We good with that? In the ballpark, right? Any questions on that? Okay. All right, the next thing to do, let's go ahead and find the axial force in that shaft. Okay, so see if you can find the axial force in the shaft. Remember, the axial force can be tension or compression. It's one or the other. I gave you both strength numbers because a manufacturer doesn't know what you're going to do with it, that shaft. They're going to tell you everything they know about it. So what you have listed on the top of that page is every possible thing to know about that shaft. It's up to you to figure out whether you got tension or compression. Okay? And you'll have one or the other. You won't have both. It'll be one or the other that you will have. Okay? We good with that? So let's find the axial force in the shaft. It's either tension or compression. All right, now to get the compression, what you want is a unit vector that goes from, I got AB there, okay? So what I did, I found the unit vector from A to B, and I also found the unit vector from B to A. I got both of them, because they're just, the signs are just different on them. So I went ahead and calculated the unit vector from A to B. So we good with that? Okay. And then to find the compression, what you want to do is to do a dot product. So the thing to do is to take your force vector and dot it with the unit vector. And when I did that, I got 3,038. Does that sound about right? We got any questions on that? Okay. Now, the sign on this, there's people are kind of asking about that or talking about it. Here's the deal with this. When I look at this, I can kind of see what this force is doing. If this is kind of like, have you ever seen like a flagpole extending out from a wall? They'll put a guy wire on there to kind of hold it up. It looks to me like that wire is going to go like that. And I think that's going to create a force like that. Y'all with me there? And that force is going to push from B to A. Is that, everybody seeing that okay? Now what that means, if that force is taking B and pushing it towards A, that looks a lot like compression to me. That's what I assume that is. So when I saw that, I said, okay, I will use the vector that goes from B to A. So I use this unit vector. Okay? Because I could see that component of the force goes from B towards A. And when I did that, sure enough, I got a positive answer. Now, had you used the unit vector that went from A to B, it would not have been a problem. You would have got a negative answer. And think of the negative as like saying, no, it doesn't go from A to B, it goes from B to A.
I just thought that's what it was supposed to do when it was compression.
Oh.
So it's in like...
Yeah, okay. There's different sign conventions. Negative is often used to signify compression, but in this case, the negative just means it doesn't go from A to B, it goes from B to A.
So if I
Which
did this on the test, like if I left it as negative, would you mark
No, I don't get too excited about that, but I might have a little thing for you to circle. Is it tension or is it compression?
Okay, yeah.
And that's what I would pay attention to.
Okay.
The nuances of how you write the numbers down.
Isn't a big deal.
Yeah, but whether it's tension compression, that's a big deal. Okay.
Which is that.
Are you okay with that?
In this problem, there isn't really tension.
Right. See, a shaft is in one or the other. It's not going to be in both. Right. It's either being compressed or in tension. It's one or the other. It's not going to be in both. So you just have to analyze compression on this one. Okay, and that's kind of what I was saying earlier, that the manufacturer will tell you what the shaft will do because they don't know what you're going to do with it. So they gave you all the specs on it. Okay? Is that good? Mm-hmm. Questions there? Okay. Okay. The next thing there is to find the shear then, if you've gotten that far. If you've got questions, don't just kind of walking around, just ask me. But, all right, so the next thing is to figure out the shear. Let's pause the recording again here. Okay, the moment would be next. Okay, so the moment is found using that cross right there. And you want to get your R vector and cross it with your F. And then once you've got that, you want to find the magnitude.
So it's all
You'll get to the moment, okay?
the tension. There was
My number is still off. I'm just gonna rewrite it.
Yeah.
I just did something else.
Once you make one mistake, fixing it, it's almost easier to start over again, you know? You don't see the mistakes once you make them once. All right, so the moment, there's the final number there. When you do the Pythagorean theorem, you get 19,343, something like that on the moment. Now the last little bit is, what can the max, so we get on the moment? Okay. Now the last little question there is, how high can the force in the cable go? And, well, you see, I do these side jobs, and when I can't figure them out, I just bring them into class and have you guys figure them out. So I don't know how to do that, so hopefully you guys can get that one figured out, okay? So I'll let you guys figure that one out. So now what do you do? I mean, I think you're always kind of used to maybe teachers helping you out. What if I don't help you out? What are you going to do? What's the one?
Go to the catering center and ask a tutor.
Yeah, well, that's one way to do it. Although I don't know if you'll find one. There's probably a couple good ones that could help you there.
Just in general or on this one?
In general, start working with each other, right? And if one group gets an answer and then someone else gets the same answer, that's pretty good. And especially if you use different methods, if you get to the same answer, that's a pretty good sign, okay? So I'm gonna let you just kind of work on that. Maybe on Wednesday, I'll take questions on it if you've got questions. I guess the advice I give you on the last part is an ounce of common sense is worth a pound of calculations, as they say, okay? So just think about it. This stuff isn't like relativity or anything like that. It's got a certain logic to it, I guess relativity does too if you're really, really smart, but I'm not that smart. But this stuff has a certain logic to it. There's a certain proportionality to how the numbers work. Don't overcomplicate it. You got to figure out which case governs, so to speak. What's the one that really governs which ones? If you kind of think of having like a turnbuckle, you know what that is, where you tighten up a cable gradually. If you keep making this cable tighter and tighter and tighter, which one of those three things is going to max out first? Is it the tension, the compression, the shear, or the moment? That's the first thing you're going to have to figure out, is which one governs is the term for that, okay? And then after you figure that out, you kind of wiggle in, and the term is kind of throw numbers at it. I guess there's different terms for it, wiggle in or throw numbers or whatever, till you kind of land on the number that would cause that shaft to fail. That's how I would look at it. And there are some kind of common sense ways to do that without getting into a whole lot of calculations too. Okay, I'll say that. All right.
If I show you what I did, can you tell me if it was wrong or not?
Oh, I don't know. All right, so this stuff will be due on Friday, okay? This problem, get it to me at Friday. It's a very good review for the test. That's one of the reasons I made it up. But it's also, more importantly, it's a review of the important 3D things that we've done here so far. So let's have a look here. Let's look at this review. All right, so what I have here, now this is available in Moodle. It's under the test review downloads if you're online. Okay, so let's just take a look at this. First thing I have is the vocabulary. You should know what those words mean. Okay, so that's new vocabulary. You should know important things here, the difference between a vector and a scalar. Vector is a Cartesian vector with x, y, and z components. A scalar is a magnitude. Magnitude and scalar are kind of the same thing. Resultant is when you add two vectors together. Projection, you should know projection along, which could be a tension, compression, component parallel to. All these things mean essentially are related terms, okay, that I'm putting stars next to. Okay. And compression. So tension and compression are axial forces. They're projections parallel to or components parallel to. Shear is perpendicular to. Okay, so a shear is a little different, right? That's a component perpendicular to. Cartesian vector, you should know, angle with the blank axis. So you should know the vocabulary. If I ask you what's the angle with the y-axis, That isn't on your formula sheet, but beta is on your formula sheet. So you should know that beta is the angle with the y-axis. Okay, moment about a point, moment about an axis. Those are things you should know the meaning of. Okay, so those words there on the right, you should know. So let's kind of look at what we did. We did 2D force components. Remember, we did that graphical problem, then we used trig and did some stuff with angles and added them up to get a resultant. But most of the stuff we've been doing here so far is 3D. So we've got unit vectors by taking a force vector and dividing it by its own magnitude. That gets you cosine alpha I, cosine beta j, cosine gamma k. Remember, if you add up the squares of those three things, that equals 1. You all remember what a double projection is? Okay, that's like that one problem, was it 141 maybe? I can't remember what problem number it was, but I had you do one of those. 143, I think it's 143. Okay, position vectors, RAB is RB minus RA. Okay, a dot product, I'm sure you'll do one of those. I'm sure you'll do a position vector. Okay, a dot product, A dot B is AB cosine theta. We use that to find the projection of a force onto a line, which is often a tension or compression. We just did one of those, right? If you take the tension or compression, add it to the shear as a vector, you'll get the total force. Okay? So I'm sure you'll see position vectors. I'm sure you'll see a dot product. The reason you'll see those is they're important, and we've done those in homework, right? Okay, we did 2D particle equilibrium. Remember that? I haven't turned that back to you yet, but you turned that in, those rings that were in equilibrium in 2D. Then we did 3D particle equilibrium, which is a little bit more of a formal process, where you put the forces in columns, you then add up the rows and set them equal to 0. We did 2D moments and then 3D moments. So you did a 3D moment today. I'm sure I'll give you a 3D moment on this test. I mean, it's not a mystery or anything. It's an important part of doing 3D stuff, so I'm sure you'll do that, okay? There's the vocabulary. All right, so that's the stuff I put stars next to are the things you definitely want to know how to do, all right? And the way you know how to do them is you do some on your own. You don't just follow along what I'm doing. You do some of these on your own to study and make sure you can do them, okay? You look at the formula sheet and see how that's formatted so you know what things look like. You get yourself a non-programmable calculator and practice with it so you're comfortable with it. I've seen this before, and don't get in this situation where I'll bring a box of calculators, but you don't want to be learning how to use a calculator while you're taking a midterm. You don't want to do that, okay? You want to have your TI-30 or your TI-36 or something like that, whatever. A simple calculator that's non-programmable. That's kind of the requirement at OSU, so I do that too, okay? But practice with it before the test, not during, okay? Okay, here's some of the problems that I just handed out. That one, can you do that one? You just take the cosine of the angles, right? You can do that. How about that one? What's that? Double projection, right? 2 angles. So we'll go through these maybe on Monday, okay? Okay, so we'll do that. What's that there? That's a force vector, right? With position vectors, you're going to have to read coordinates and get the force vector, right? Here's a couple just fine position vectors and unit vectors. Okay, so again, you got to read the coordinates. You're going to show your work on those if you have to do anything like that. So if you bust a sign, I'll be able to follow it, right? So you know when you're taking this test, you're doing the work, but you're also giving me work I can follow so I can grade it, because you're going to take precautions if you drop a negative, that then I can see what happened, okay? That's your responsibility, right? Okay, we're going to find the compression in AC caused by FAB. How are we going to do that? What's the operation for that? Dot product with a unit vector, okay? Then we're going to find the moment about moment about C. That's a cross product, right, with a position vector for the moment arm. Yeah, question?
So from what we were kind of discussing earlier, when you're trying to find, if you go back, the unit vector of, I think it was AC.
Okay.
So do you always do you always want us to find, like, if it's a beam A to C?
I don't really care on a dot product. I don't really care because the only repercussion of switching the letters is you'll get a negative sign.
Yeah.
It's not that significant, really. So you could do it either way. Usually I kind of start where the force is and go the other ways.
So like the point of the force vector is
Yeah.
where you usually start at?
Yeah, normally, yes. And then, yeah, okay. Okay, there's a moment vector, which is a cross. What's that? We've got resultant, so you add the two vectors together. So you need to find the vectors. One's with angles, the other is with positions. Notice, even though I'm not at the origin there, I can still use the angles with the x, y, and z axes. What else? Okay, there's a 2D equilibrium problem, okay? So for sure you can do position vectors, you can and find a force, you can do dot products, and you can do crosses. For sure you want to be able to do that stuff. Don't study anything until you get that figured out. That's the most important core stuff right there, okay? All right? All right, we can go over this review on Monday, the problems and things, okay? And this other problem we did today is due Friday. We'll review it. If you got questions, I'll take them on Wednesday.